For over half a century, our relationship with space has been defined by the explosion. To reach orbit, we sit atop massive cylinders filled with volatile chemicals, burning through millions of pounds of propellant just to nudge a small capsule into the vacuum. It is a violent, expensive, and fundamentally inefficient process. But there is another way, a method governed not by combustion, but by structural engineering and the steady pull of orbital mechanics. This is the space elevator, a slender ribbon stretching 60,000 miles into the sky, allowing us to simply drive into the stars. The idea isn't as modern as it sounds. In 1895, the Russian physicist Konstantin Tsiolkovsky visited the newly completed Eiffel Tower in Paris. He wondered if a structure could be built so tall that its top reached into the weightlessness of space. Tsiolkovsky realized that if you could build a tower high enough, the centrifugal force of Earth's rotation would eventually counteract gravity. While his initial vision of a freestanding tower was physically impossible due to the compressive strength of stone and steel, he laid the conceptual foundation for a tether held in tension. To understand why we need an elevator, we have to look at the rocket equation. In conventional spaceflight, a rocket must carry all the fuel it needs to lift its own weight, plus the weight of the fuel it will use later. This creates a diminishing return, where 90% of a rocket's mass is often just propellant. To get 1 kilogram of cargo into orbit, you might need 20 kilograms of fuel. An elevator bypasses this entirely. By using a permanent structure, we can power the climb using external energy sources, like lasers or solar arrays, making the cost of transport comparable to a long-haul flight. The physics of the elevator relies on a delicate balance of forces. Imagine spinning a ball on a string. The string stays taut because the ball wants to fly outward. This is centrifugal force. In a space elevator, the string is a long tether attached to Earth at the equator, and the ball is a massive counterweight located far beyond geostationary orbit. At 22,236 miles up, a satellite orbits at the exact same speed that Earth rotates. By extending the cable past this point, the outward pull of the counterweight keeps the entire ribbon under constant, stable tension. Building this stairway requires a material unlike anything we currently use in construction. The primary challenge is tensile strength. A cable stretching 60,000 miles would have to support its own weight, plus the weight of the climbers. If we used high-strength steel, the cable would snap long before it reached orbit. Even Kevlar and carbon fiber, which are remarkably strong, fall short of the required strength-to-weight ratio. We need a material that can withstand roughly 50 to 100 gigapascals of tension, essentially a material that is 100 times stronger than steel but much lighter. This is where carbon nanotubes enter the picture. Discovered in the late 20th century, these are cylindrical molecules of carbon atoms with a hexagonal lattice structure. In theory, carbon nanotubes possess the necessary strength to build a space elevator tether. They are incredibly light and have a theoretical tensile strength that matches our requirements. However, the hurdle remains in the manufacturing. Currently, we can only grow these nanotubes a few centimeters long. To build an elevator, we need to weave these microscopic tubes into a continuous ribbon tens of thousands of miles long without introducing structural defects. While carbon nanotubes are the most famous candidate, researchers are also exploring alternatives like graphene and boron nitride nanotubes. Graphene is a single layer of carbon atoms arranged in a 2D sheet, boasting even higher strength than nanotubes. Boron nitride, sometimes called white graphene, offers similar strength but with better thermal and chemical stability, which is crucial for surviving the harsh environment of the upper atmosphere and the radiation of the Van Allen belts. These materials are currently being refined in labs around the world, moving from microscopic flakes to increasingly larger, more coherent structures. Once we have the material, how do we actually build it? We can't build it from the ground up because it would collapse under its own weight. Instead, we must build it from the top down. We would launch a spacecraft carrying a spool of the tether material into geostationary orbit. As the craft unspools the cable toward Earth, it also moves a counterweight in the opposite direction to keep the system balanced. When the lower end of the tether reaches the surface, it is anchored to a massive floating platform at the equator, creating a permanent bridge to the stars. With the tether in place, we introduce the climbers. These are mechanical vehicles that grip the ribbon and ascend at speeds of several hundred miles per hour. Unlike rockets, they don't need to carry heavy fuel. Instead, they could be powered by ground-based lasers aimed at photovoltaic cells on the climber's underside. This allows for a smooth, quiet journey. The ascent to geostationary orbit may take several days, but the experience would be more like a cruise than a heavy lunch. Passengers could watch the Earth shrink away in total silence, protected by the structural integrity of the ribbon. The economic impact of a space elevator would be transformative. Currently, it costs thousands of dollars to put a single kilogram into orbit. An elevator could drop that price to under $10. This shift would change space from a restricted frontier for governments and billionaires into an accessible domain for industry and research. We could easily transport the materials needed to build large-scale solar power satellites, massive space telescopes, and permanent lunar colonies. The elevator doesn't just get us into orbit. It creates a logistical pipeline that connects our planetary economy to the resources of the solar system. There are, of course, significant risks to manage. Space debris and micrometeoroids pose a constant threat to a static tether. A collision could potentially sever the line. Engineers propose using a ribbon-like shape rather than a circular cable to minimize the impact of small punctures, along with active tracking systems to move the tether out of the path of larger debris. Furthermore, the cable must be able to withstand the intense electromagnetic forces generated as it moves through Earth's magnetic field. These are not insurmountable problems, but they require a level of precision engineering we are only just beginning to master. The space elevator represents the transition from the era of exploration to the era of settlement. By moving away from the limited physics of rockets, we can build a reliable, sustainable bridge to the rest of the universe. It is perhaps the most ambitious engineering project ever conceived, one that requires us to master materials at the atomic scale to build a structure at the planetary scale. When the first elevator is finally anchored, the sky will no longer be a ceiling. It will be a destination, accessible to anyone who chooses to push the button and wait for the doors to close.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.